Okay, so we're going to shift now from doing regression-based models to classification models. So if you remember in this class, the difference here is only that classification algorithms are used for dependent variables that are categorical versus the numeric dependent variables. So let's take a look at all of our options here. Quite a few more, but they're not really a whole lot more complex. It's a lot of the same basic ones, but they're divided up into these two-class versus multi-class. So two-class again just means that the outcome variable has two possible options, like with our bike buyers data here. It was coded initially as yes and no. Now we could leave the data as a 1 and a 0 and use a two-class model, and it would simply treat that 1 and 0 as text and still classify it as one versus the other, and we wouldn't get a range or a decimal point prediction like we did with linear regression. But anyway, then these multi-class are those that have more than two outcome possible values. So that one would be like the lending tree data example we did, where we tried to predict whether they were going to be current, fully paid, charged off, default, late, 15 days, like 30 days. There's a bunch of different possible outcomes to predict. So let's start with the two-class models, and we're going to simply get rid of our regression model, and let's begin with logistic regression. This is the simplest one, and what we need to do is change the columns we're selecting. We're no longer going to use this purchase bike numeric variable. We're going to switch to the original purchase bike yes no variable, all the same other variables. So let's check our box. Train model, we got to change this because this still is trying to select purchase bike numeric, but that doesn't exist. So again, don't stress that it shows all these other variables that we supposedly eliminated with our select columns. It's doing that simply because we haven't rerun this new, we haven't rerun the select columns yet with the new values, and so it's pulling in everything because it doesn't know better. Anyway, select purchase bike, hit OK. We still have our original data set, our column selector. We're still normalizing numeric variables. So now it's no longer going to normalize a dependent variable because it's not numeric to a z-score, that is. Same split, we treat it just the same. Train model the same, score, evaluate. Evaluation is going to occur differently. You'll see in just a moment. So let's go ahead and run this. I'll pause. Okay, here we go. Let's take a look at our train model. Visualize. We still get our feature weights, or in other words, our coefficients, just like we did with the logistic regression. We have some other settings here that apply to logistic regression, but we're not going to worry about those for now. Again, cars is our biggest weight here. So people, the more cars you have, the less likely you are to purchase a bike. Next, those who live 10 miles away or more are less likely to purchase a bike. People with a lot of income are more likely to purchase a bike. That's how we interpret those, because they're negative versus positive. Once again, we have our kind of our baseline dummy codes for each one of our categorical variables. It's showing us how it's coding those down here. Let's close that out. Let's evaluate model. Oh no, let me show you score model first, just so you can see how this is different. Remember, with the regression models, we got a scored label, and that was a percentage between 0 and 1 because our dependent variable was between a 0 and 1. Now the scored label is in the form of our dependent variable, purchase bike. So it's going to be a no or a yes. But we get, along with that, the probability or likelihood of that no or yes. So it's very similar to what we were getting out of the regression. It just divides that scored label into this. So if you'll notice here that anything, I'm guessing here, and 37% no, we could convert that into probably right back into the same scored label we had before. But anyway, so yep, that's what we get. Evaluate model, let's take a look at that. Visualize. Okay, this is a chart that I like a lot. Let me show you what these things are down here. We get, instead of r squared and root mean squared error and things like that, we get the number of, it gives us this accuracy matrix that a lot of you have seen my students calculate this on their own back when we were doing linear regression. So for positive labels, yes, or for the label yes, we got 88 true positives, 45 false positives, and you get the idea here. And then we get these accuracy and precision scores. So what I want is to copy accuracy, and we're going to treat that as our effect size now. Now let me pull up. This was our Excel spreadsheet where we're keeping track of those models before. Let's insert a bunch of stuff here. And let's start running. So this will be our, we'll call this one our bike buyers data. Let's merge and center that. So with our logistic regression, we're going to start comparing our models here. We get, let me pull this down. So our accuracy is, did that work? No, it didn't. 0.643. All right, do I want to keep track of anything else? Let me see here. Precision. Do I want to keep track of that or no? Yeah, I guess I can. So what is precision exactly? 1 second here. 2. Okay, I think the best way is to show you right here. This is a great resource for explaining how to evaluate these various models. Let's start with accuracy. So accuracy is simply the proportion of correctly classified instances. So that includes both true positives and true negatives. All right, in our case, that's a total of 64%. So you might be more concerned just about true positives though. So in this case, we've got precision and recall to both analyze that. So here in their example, they're just applied this to ours. Precision is out of the individuals whom the model predicted to be earning over the 50,000, or in our case, out of the individuals whom the model predicted to buy a bike, how many were classified correctly? So that's not counting the false positives. This is out of just the true positives and false positives. Sorry, not counting the true negatives. Then recall is a slightly different question. Out of all the high-earning employees with this income, how many did it classify correctly? So they're very similar. So this is the true positive rate. And then here, actually looking directly at the formula is a easier way to see that. True positives divided by true positives plus false positives. True positives divided by true positives plus false negatives. Anyway, they're all useful. What I like right here is this, is the curve of false positives. So a good way to interpret this curve, they call it the ROC. The closer this curve is to the upper left corner, the better the classifier's performance. So what we want is more area between this curve and this line right here, which is random guess. No accuracy whatsoever is what that represents between the true positive rate and the false positive rate. The closer it is to this side, the better our accuracy will be. And you might think of this as the more area under the curve, the more money we make. So you can also use that curve in other ways, but I'll hold on to that one for a little bit later. Anyway, back here, that's how we interpret classification model performance. Here's our curve with our bike buyers data set. So the maximum, the largest distance from the curve is right around here somewhere. You might think of this as where we get the most bang for our buck. So for example, if I were to use this prediction to sort based on that probability, remember we're given a scored label and a scored probability. If I sort all my data by the scored probability and say, all right, how many of these people should I approach to try to sell a bike to have the biggest bang for my buck? Meaning if I go and try to sell a bike to everybody, there's no point of prediction whatsoever, right? Because they're either going to buy a bike or they're not. But if I want to go after only a portion of the population that's most likely to purchase a bike, then I want to rank sort them by scored probability and go through, let's see, this spot is the biggest, furthest away from the curve. Then I want to go to the first 37% of my rank ordered by scored probability cases and try and sell a bike to them. Because every person after that, I'm less likely to predict accurately after that. Anyway, we'll review that one again later on. So that's it for logistic regression.